All right, so here we are. Hi, everybody. Nice to see your faces. Let me share the screen. This one. Okay, cool. So, first of all, good afternoon, and I hope that you all had some time to chill and relax and to, get everything that you need and that things are under control and everything. And yeah, as I said, we're gonna try and we're gonna make this course flow as okay, of course, not as it usually would, but we're gonna try and make it flow as smooth as possible. And basically, from now until the end of the semester, we're gonna do things remotely like this. So all the things are going to be online. I will be on Zoom on some other times during the week, so you can come and talk to me, and we can chat about the course, about solar physics, about everything you want. And today the idea is to do a hands-on exercise, and the hands-on exercise is going to take us on a journey where we will go from the given model atmospheric model, which in this case means very, very basic atmospheric model, which means we are going to rely only on temperature and gas pressure stratified on some height grid. And we're going to go from there and use as simple physics as possible, but not too simple, to try and calculate something. And of course, there will be a lot of limitations there. We'll discuss them, and I will try to make additional notes in this Jupyter notebook as we are after the class, and then update it so that you can see all the additional comments that we all together made, and as we discuss what is going on here. So as I said, the easiest is if you just clone everything. In there should be a Jupyter notebook. There should be a dot file, which is called FALC.dat, which contains our basic atmospheric model. And then there are two FITS files, which contain various data, and we will encounter the data as we go through this exercise here, which contain various data about 6301 and 6302 lines of iron in two different model atmospheres. So you will see that there are the response function values, opacities, emitivities, spectra, atmospheric models, everything. So in case that we have the time today, we can try and do some of these things, take a look at there. If not, some of these things are going to be in your homework. Yeah, so as I said, bear with me. I know that you won't be as interactive as you usually are, but still, don't hesitate, interrupt me, write things in chat. Just try to participate as much as you can, and feel free to go ahead. If you already know what I'm going to do and you understand it, try to go ahead, play, experiment, do whatever you want. Right? I'm gonna go slowly. I'm gonna describe every step. I'm gonna spend some time discussing what we missed, what is more complex, and so on and so on. Okay, so as I said, the goal is to go and to try to all radiative transfer process and calculate all the needed quantities and finally obtain the spectrum of the given line. Okay, so what we're going to do is we're going to start with, and now I can mark the things very well. I'm going to start by loading this atmospheric model. Okay, and the fact that I'm skipping row 1 just means that I already know how the model looks like, and I know that basically row 1 is some redundant, some unnecessary text which I can skip. So the actual data is from the second row, and you will know that if you open this FALC in any sort of editor. And today we're gonna, to your huge joy, I guess, we're gonna work in SI, system of units, and that's gonna take some transformation because most of the codes today, probably because of the historical reasons, provide all the data in CGS. One of the exceptions to that rule is RH, radiative transfer code, written by our colleague Han Wittenbroek. And he actually was kind enough to write his code completely in SI, which means that to somebody facing it first time, it's much more clear. However, for other people who work in CGS, comparison is not as trivial. So basically, what you need from this atmospheric model, we can go later and discuss some other quantities, is the first column. Okay, so here I'm using the notation in Python indexes. So it's the second column, the column with index 1, which contains a height grid in the given atmosphere in centimeters. Then the third column contains temperature, and the fourth column contains gas pressure, right? So this model atmosphere is exactly what I told you before, that usually model atmospheres are, they're just tables with some contents, with some data that we need to describe the atmosphere, right? And here we are only for the moment interested in temperature and pressure, gas pressure, on the total height grid. Why I'm saying gas pressure? Well, because sometimes in some regions of the solar atmosphere and solar interiors as well, radiation pressure can also become very important. So what I'm going to do here is I'm gonna give specific names to height and temperature, just so that we can understand better what's happening in the code. I'm going to convert the height from centimeters to meters, and then I'm going to plot the temperature run with height. And here I divided the height with 10 to the 3 to make it in kilometers, because we are most used to kilometers. So here on the left-hand side you have the photosphere. On the right-hand side you have, I would say, chromosphere. So this specific model doesn't go to corona, doesn't even probably go to transition region, but you basically see the beginnings of the transition region in this very sharp jump in the temperature here. So this is where temperature is going to start increasing very, very steeply, and it's going to go to millions of kelvins. So you see here that the temperature decreases from the photosphere, reaches this temperature minimum around 500 kilometers, and then starts increasing as we go to the chromosphere. And this is one of the so-called semi-empirical atmospheric models, which means that it was tuned finely to reproduce many aspects of the spectrum. So Dennis can tell you more about it, as he actually did some of these fittings by hand using many lines in his stellar atmosphere work. But this is a very painstaking process, and people spend a lot of time obtaining these. And these are very carefully constructed, so that's why we use these atmospheric models for a lot of our preliminary studies. And I'm showing you today so that you can understand how the lines that you are going to use for your diagnostics are formed and what quantities come into play there, but also because sometimes before your observation or after your observation, to understand something that is happening there, you need to do this sort of modeling. And to sort of understand what sort of parameters influence your line formation. Okay, so now the next step that I want to do is I have the total gas pressure, which corresponds to total number of particles. So as long as the gas is ideal, meaning that it's not degenerate, the total gas pressure is equal to the total number density of particles times K, well, K is Boltzmann constant, times the temperature, right? So what I'm going to do here, and actually let's start executing these. So I'm going to execute this import. I'm going to execute this. There is the plot again. Everything is going to look the same as originally, but just maybe we will want to change something on the way. So for start, it will be clearer if I use the temperature here, although it's the same. And then we're going to do this plot. And here you see how the total particle density, so number of particles per meter cubed, decreases as we go from the photosphere, which is always on the left, and this sort of plots to the chromosphere on the right. And you see why gas pressure is so, and why solar atmosphere modeling is so hard. It's because the density, the pressures and the densities correspondingly change by 6 orders of magnitude as you go through the atmosphere, and that's a lot. And if you want to go up to the corona, it's going to get to even smaller particle densities. So that's challenging, right? But you see that the particle density in the log scale is almost linear, and we have taken a look at that and we have explained that before. So now actually I want to solve this situation that we had before. What I want to do now with the exercise, I want to try and calculate spectrum of the H alpha line. And don't laugh, you all know that H alpha is actually much harder than we think it is, but we're just going to try. We're going to make a lot of mistakes, but we will understand what mistakes we are making, right? And this is sort of the idea of this is to show you the process. And unfortunately, except for its non-LTE effects, actually, fortunately, except for the non-LTE effects, hydrogen is relatively easy to treat because it's very simple. So the easiest thing that I can do so that you can understand every step is to treat only the hydrogen. If we wanted really to like calculate the spectrum of iron line or something like that, we would have to use some steps which we wouldn't fully understand. So I will show you now how to do these things in the case of hydrogen only, and then later you can maybe understand, or if you're really interested, you can try and write more complicated code that is going to do it for more complicated atomic lines. So what we want to do, and we discussed this already on the whiteboard a couple of lectures ago, we want to solve the We want to solve for ionization stages. So we know that hydrogen H alpha is a line of neutral hydrogen, but what I have here is the total number of all particles. And total number of all particles means neutral hydrogen, protons, and electrons. And you should probably, doesn't matter what you should know. You are already guessing that there is some system of equations which needs to be solved. And I hope that you understand why these three equations are needed to, are going to appear. So first of all, we have hydrogen only. So number of electrons needs to be equal to the number of protons because plasma is neutral on average. And then the sum of all these particle densities needs to be equal to the total particle density. And these are two equations. The third equation is basically the Saha equation, which relates the densities of protons, electrons, and neutral hydrogen through some function of temperature. And this is where we get to the nonlinear problem. So that is already for hydrogen only, the problem is nonlinear. And I will let you derive this, solve this nonlinear problem. You will see that it's basically a second order equation, so quadratic equation. We all, of course, only take the positive solution. And here in this chunk of code, I'm solving for that. So I introduce some constants here: Planck, Boltzmann constant, Planck function, electron mass, speed of light, and so on. And I basically calculate some quantities here, and here there is a solution where I solve for electron densities as an unknown parameter. And then I know the relationship between the electron densities and neutral hydrogen, where basically NP is equal to NE, so I have NE squared over NO equals to this function of temperature. So then I can calculate the amount of neutral hydrogen as NE squared over this thing here. So here I use some shortcuts. I will ask you to just go and derive this yourself. If you have problems understanding this specific block here, you can come back and talk to me, and we can discuss how these things came to be. And then what I'm going to do is I'm going to plot something different this time. I'm going to plot the ratio between the electrons, which is same as the number of protons, and the amount of neutral hydrogen. So this is basically going to show us how much the hydrogen is ionized through the atmosphere. And please note that I'm assuming Saha equation here, which assumes that hydrogen is only, that basically all the ionization balance is determined through collisional processes. We know that for the higher regions of the atmosphere, that is not true because the radiation becomes important. Okay, and but this is the only thing that we can do now in 1 hour. If we wanted really to take into account everything, we would need weeks, maybe even months, even in the simplest possible case. But this will still give us a lot of insight. And you see now something that we have already seen before is that the ratio between the electron number density and neutral hydrogen number density is very small in the photosphere, but then drops even more down, but then starts increasing. And even though the higher regions here have the same temperature as the regions in the deep chromosphere, the ionization is much larger. And we explained this, and we said that this is because, this is of course the nonlinear dependency, but intuitive way to understand this is to say that this is because the densities deep in the photosphere are higher and the recombination is more likely. Do you remember this? I guess you do. Okay. Okay, so I guess I forgot to execute some of these things. So let's execute this, let's execute this, let's execute this. We got the same plot, that's great. And now we have the amount of neutral hydrogen, which is something that we need, right? So now is we need to calculate, because remember what we need for the radiative transfer, to solve the radiative transfer equation are the opacities and emissivities, right? And we are treating H alpha line here, so we need the level populations of the levels 2 and level 3. Okay, so the easiest thing that I can do is I can assume that Boltzmann equilibrium holds, and that level populations are following Boltzmann distribution. Again, for H alpha, this is a bad assumption, because again, Boltzmann, the distribution assumes some collisional balance. That collisional balance is not true in the high regions of the atmosphere. because the radiation and collision start competing, and in the end we're going to get the wrong shape for H alpha, but that's not what matters. What matters is to go through this process. Okay, so what I'm doing here now is I basically went to NIST. I took the energies of second and third level of hydrogen. I took their statistical weights. Sorry about this, which you probably know. And then I'm using Boltzmann distribution, right? So what is the Boltzmann distribution? Let's remind ourselves what it is. Well, that says that basically density of the state I is equal to total and so excitation state I in the ionization state J is equal to the total number of particles in that ionization state J times statistical weight of the state I e to the minus EI over KT, and here I have partition function. How did we denote partition function? Can somebody remind me? Do you hear me? Z. Okay, Z sounds good, Momo. So let's do something like this. And then I'm going to run this. And okay, so NJ we just calculated. GI, actually this should be GIJ to be completely consistent. JI, and this should be JI. Okay, so we just calculated NJ, that's the number of neutral hydrogen. We know statistical weight, we know energy, we know Boltzmann constant, of course, we know the temperature. What about Z? So Z is the partition function of the given ionization state. What about that? What should we do about that? Can somebody tell me that? If you are shy to speak, feel free to write in chat.
Maybe we have to normalize it such that the sum over all the i's add up to 1.
Yeah, in a way, yes. So in principle, the partition function is the sum over all i's of this this term up here, GJI e to the minus EJI over KT. That would be ZJ. However, that's very cumbersome. That means that you need to take into account all the atomic levels and sum them all up. In practice, for arbitrary species, so let's say iron, sodium, whatever you're treating, you have polynomial approximations for this that you can find in some papers online. And I'm going to link in lecture notes one of these papers. These things are very, very handy. So at some point, people realize we need this, and some very nice and very diligent people calculated these things for us. And now we just go to that and we implement these things in our code, and we have the partition functions. For hydrogen, we can approximate that it's equal to. Why is it justified for me to assume that it's approximately 2? Well, because in all these sums, there is this term e to the minus energy over KT. All the hydrogen levels are lying very, very high over the ground state. So basically, partition function is dominated with this term in the ground state, and by far most of the electrons are in the ground state level. So basically, my partition function is approximately going to be equal to the statistical weight of the ground level, which is 2. You can try that out. Try to do that, and you will figure that it's almost 2, no matter, unless you take some ridiculously high temperature, which should be, I don't even know how high. Now you will always get that partition function is almost equals to 2, and that's why I'm dividing here by 2. Okay, and after I calculate these two things, I can plot the population of these two levels, and they look like this. And you probably remember this plot from 2 lectures ago. We have this dip of energy population around the temperature minimum. So even though the particle density is much smaller in this, let's call it mid-chromosphere, which is something between 1,000 and 1,500 kilometers, the populations of second and the third level are still higher than in the temperature minimum, because in temperature minimum, the temperature is so low, you can't get enough. And that's by the temperature, you cannot get enough hydrogen of second and third level. And that's why we say that, and I think I have shown it in my talk before the class last Tuesday, that's why these regions of the temperature minimum are basically transparent for the H-alpha radiation. And that's very, very interesting effect. So now I have these two level populations, and now I can use the equations to calculate opacity and emissivity. So before everything else, let's put in the equations for opacity and emissivity here. I'm going to take a few minutes and I'm going to write them down. So for the emissivity, which depends on lambda, you remember what it was. It was proportional to the number of number density of excited atoms, which I'm going to denote with N3. Then Einstein coefficient of emission, which I'm going to denote with A32. Before I used U and L for upper and lower. Then there was this constant which accounted for energy of one photon. So I'm going to use HC over lambda, and there's going to be a line profile, right? Okay, this looks good. So now let's do the same for opacity. So for opacity, it was very similar, except I had here N2 B23 minus N3 B32, and this minus here stands for the stimulated emission. As we have said, the stimulated emission is basically just negative absorption, right? So, oh, sorry, this is not J, this is chi. Okay, so important thing here is that now, contrary to the quantities we dealt with so far, which means number densities, temperature, pressure, and so on, which only depended on height, opacity and emissivity depend on height and on wavelength, right? So they are going to be 2D arrays now. And also, another thing is that now I have to take into account the fact that I need to somehow model this phi lambda, which is something that we call the absorption line profile. So what I'm going to do here is I'm going to make an array of lambdas, which goes some 10 angstroms around where I know that my H alpha is. H alpha is around 655, 62.8, something like that. And I'm converting it to meters here. I'm using like 400 points for the line profile, which should be enough. And then one completely unintuitive step, which you maybe didn't think about by now, is that usually when we talk about the wavelengths of the spectral lines that we see in the atlas, as long as these lines are in infrared or in optical, these are the air wavelengths. So the way we see them here. However, the wavelengths between measured in air and measured in vacuum are slightly different, because air has a slightly higher index of refraction than 1, while vacuum has 1. So first thing that I need to do before all the calculation is I need to convert these lambdas that we are considering, observing, I need to convert them to vacuum ones. And then we're going to solve everything in vacuum, and we're going to go back to the observed air wavelengths, okay? I'm going to create these two variables, which are going to be two integers, which are saving basically the lengths of these two arrays. I'm going to calculate the line center wavelength, which is basically HP, which I use to denote Planck constant, times C over the difference of energies in joule. And finally, there is mass of hydrogen that we will need to compute the temperature broadening, right? So you remember that basically this shape of the spectral line here is determined by the various kinds of broadenings, and so this phi lambda, and we're going to try to take into account what we can today. We can't take into account much, but we'll try to do some things. Okay, and also before calculating opacity and emissivity, I'm gonna calculate Einstein coefficients. So the way I did this is I went on NIST webpage. I examined, I found the Einstein coefficient for spontaneous emission, which is 4.4 times 10 to the 7. Remember that I told you for most of the lines it's something between 10 to the 5 and 10 to the 8. So H alpha is a relatively strong line. This is a relatively high value for the Einstein coefficient. And then from that, I'm calculating the Einstein coefficient of stimulated emission and Einstein coefficient for absorption. And I think I made a mistake in one of the previous classes. So if you find this equation here, so the ratio between the Einstein coefficient for spontaneous emission and stimulated emission, instead of B32, I use B23, or instead of B upper lower, I use B lower upper. I will also put a link to some page dealing with Einstein coefficients. Even on Wikipedia, you have very reasonable explanations. So don't hesitate, just go and take a look at it. But basically what we need to understand here and what we need to remember here is that if we know one of the Einstein coefficients, we can calculate all three, and they're just related through some physical constants and some properties of the levels. So they're really, Einstein coefficients are really constants. They don't depend on temperature, they don't depend on pressure, and so on and so on. And now I have everything, almost everything that I need to solve these two equations for opacity and emissivity. I only need the line profile. Okay. And what I'm going to do is I will have a different line profile at each depth because the broadening is going to be different at each depth. So what I'm doing here now in this block of, so let's also execute these so we are completely consistent. And actually, yeah, now I can print these for you. And what I want you to pay attention here is that the magnitudes are severely different, and Einstein coefficients B are much smaller because they're going to be multiplied by the intensity, and then they're going to have similar order of magnitude as Einstein coefficients for spontaneous emission. And of course, it depends on how are you defining your intensity. So if we defined our intensity here, instead of per wavelength, if we denoted it per frequency, which is what you will find in most of the textbooks, I just prefer working in the wavelength here because it makes things easier to relate with the observations, then these numbers are going to be completely different, except for A. A is in hertz, and that's always the same. But B will depend on how you are defining your intensity. Okay? So now we are calculating opacity and emissivity. And what I'm doing I'm going through the atmosphere. At each depth, I'm going to calculate the Doppler velocity. And Doppler velocity, since I'm dealing only with one line, then it only depends. I mean, the Doppler velocity is going to be different for each atomic species. Here we are only dealing with one line, so I just need to calculate the Doppler velocity as square root of 2 kT over mh. Later, we're going to change this mass, and we're going to see how our line changes, okay? And then from the Doppler velocity, which is going to be something in kilometers, and this is going to be order of view, maybe 10 kilometers per second. Then from that, I can calculate the Doppler width, which is going to be what? Where it's going to be, it basically tells me how much Doppler shift this kind of velocity here, dvd, is creating, right? And it's going to be, I'm going to call it DLD, like delta lambda Doppler, is going to be wavelength divided by c times the Doppler velocity. And then I can calculate the profile as a simple Gaussian. And we know that Gaussian is 1 over square root of pi divided by sigma e to the minus x squared divided by sigma squared. So basically x for me is this quantity here, lambda minus lambda 0, right? Okay, and this is the profile. And yeah, we can plot actually one of the profiles. Let's say if let's say somewhere in the middle, if d equals 30, we can do PLT figure, fixed size. I like 10.7, it works well here. PLT plot. I'm gonna do lambda profile. Okay, then I'm gonna write this down and see the profile. It's actually very narrow, and I will just multiply the lambda here with 10 to the 10 to get it in angstroms. Okay. Right. Don't be confused by this huge magnitude of the profile here, right? I'm dividing here with delta lambda d. But when I integrate, this profile is going to be 1 because these coordinates here are actually much smaller. They're multiplied by 10 to the minus 10. Okay, so profile is very, very narrow. But we will see later that it doesn't mean that the line completely is going to be very, very narrow. Cool. And then finally, I can calculate opacity and emissivity at each depth by doing what? By basically just writing down these things that I'm going to zoom this a little bit more. Maybe like this is better. It looks a bit small to me. So this is basically just me translating these two equations here, translating them in opacity and emissivity. So thanks to the Python creators, I can just multiply things at vectors. So opacity at point D is an array of length equal to the number of wavelengths, and and the profile is the same. So once again, here through these equations, you can clearly see that all the wavelength dependence of opacity and emissivity comes from the line profile. Okay, so now we have opacity and emissivity because of the spectral line processes. Okay. And now just to verify things, what I'm going to do here is I'm going to calculate the Planck function at this wavelength, and I'm going to compare the source function that I get from these opacity and emissivity with the Planck function that I'm obtaining, and they should be the same, right? And I just want to, before that, stress one thing, since we plotted the profile here, is that far from the line core, opacity is basically 0. And this is, among other things, because we assumed Gaussian shape, and Gaussian really, really quickly drops to very, very small quantities. And we will see that in the end, our line profile is going to be very weird because of that, and we'll try to do something to fix it. Okay? Cool. So now what I'm going to do is I'm going to calculate the Planck function, which we usually call B. What I meant is this is Planck function, and I'm using the definition that uses the wavelength, so it's 2hc squared over lambda to the 5 times 1 over e to the hc over lambda kt minus 1, right? And then this is going to be, I'm going to have one value of the Planck function for each depth, and then what I'm doing here, I'm picking some random wavelength. I took 200, but we can also take one more. We can take, for example, 0. See if everything's okay. And what I'm plotting is I'm plotting the ratio of emissivity and opacity, which is the source function, and I'm plotting the Planck function here. And when I plot these things, you see that all these things overlay on top of each other. And this might be shocking to you, but this makes a lot of sense. And actually, you can use this to calculate this relationship between the Einstein coefficients. And the reason for this is that we have assumed something called local thermodynamic equilibrium. And all these distributions that we used, Saha distribution, Boltzmann distribution, blackbody radiation, they're all consistent with each other. So no wonder that the ratio between the emissivity and opacity calculated in LTE follows the Planck law. So far everything seems okay, and we are very happy. So we have opacity emissivities, we have the heights, we are almost there at the moment where we can solve the radiative transfer equation. Still not yet. There are still some things to be done and some additional reality chunks to be introduced. So good. What I'm going to do now is you remember that the source function, the form of the radiative transfer equation that we want to use is the one that uses the source function and the optical depth, right? And by optical depth, I mean monochromatic optical depth, which means optical depth at given wavelength. So what I need to do now is I need to basically calculate the optical depth scales for each wavelength for my whole atmosphere in order to be able to understand what is happening here. And the way that I'm going to do it is, let's add that, we know that optical depth at given wavelength between 2 points is integral from 0 to the total path, let's say, of opacity something like this. Does this make sense? Sorry, I'm missing prime. Okay. So the optical path between the optical depth on distance corresponding to some distance s is the integral of the opacity times the elementary path. right? And the way that I'm going to do it is I'm going to make a new array, which is called tau, which again has dimensions number of depths times number of wavelengths, because I need to see how my optical depth changes with depth. And that's going to be different for each frequency. I'm going to start from 0 on the top boundary, and then what I'm going to do is I'm going to move down, and my optical depth in point D is going to be the optical depth in the previous point plus, and this chunk here describes basically what we call Euler integration. And I just used absolute value here for height so that I don't have to think with how are the heights ordered. In principle, I didn't need this, right? So this just says take the mean opacity and multiply it by the distance in height, right? Now a question for you. I could have done also this. So instead of using arithmetic mean, I could have used geometrical mean. Can somebody tell me why would geometrical mean here make more sense or less sense than the arithmetic mean? Are you all asleep? Somebody has to have an idea.
It's because the geometric mean does an interpolation on a log scale, whereas the arithmetic mean is like doing a linear interpolation, essentially.
Exactly. And exactly. Way to go. Yeah. So we know that opacity doesn't behave linearly. It basically, the most important scaling for opacity, well, maybe not the most important, we have seen it up there, but if everything else is constant, opacity drops with density, and density drops exponentially. So interpolating in log scale, which would basically correspond to, geometrical mean, would in this case maybe make more sense than the linear. However, you can always assume and say, well, hopefully my atmospheric model is fine enough that I can just use arithmetic mean, everything is going to be fine. For the previous plots, I used the geometric mean. Let's, for the lols, as they say, let's use the arithmetic mean to see what happens. Okay. So what I'm going to do now is I'm going to check what are the magnitudes of these optical depths that I'm obtaining. And what I'm doing here is I'm plotting the optical depth, right? So I'm plotting how the optical depth changes with height at my point, which is furthest away from the line core, which is basically 0.0. So where the opacity is very low. Okay. And I'm going to do that now. And there is a very important thing is that the opacity there, so the optical depth there is still very, very, very small, okay? And the fact that this is, are these my earphones? Can somebody say something just so that I know that my earphones didn't run out of battery?
Testing.
Okay, thank you. Hello. I'm just gonna change my earphones. 1 second. In the meantime, while I'm doing that, you could think about why is this optical depth in the line wing so small. So what we are getting here is that at the bottom of the photosphere, the total optical depth is 10 to the minus 100, which is ridiculous. So think about it, and I'm just going to change my earphones. Okay, does anybody have any idea? No ideas. Hmm? So do you hear me still? Just checking if I didn't break anything with this.
I hear you.
Okay, cool. So actually, yeah, these earphones are not good. I'll just use my. Okay, so the reason for this is that exactly what I was showing you previously on the plot of the line profile. We only took into account line processes. The region of the photosphere is very thin. Well, it's not. It's always the same. It's just the reason here is that we only took into account line processes, and we modeled the line as Gaussian. Gaussian drops very quickly with wavelength. So number here at the edge of the wavelength grid for the line profile are super, super small. And even when I add these things together, I'm adding something very, very small. So the real explanation would be that I'm missing some opacity from other sources. And I said I didn't want to go into this when we talked about the theory, because you already know that roughly there are other sources which are contributing to the opacity, and these are scattering on electrons, scattering on molecules and atoms, famous H- opacity, bound free opacity, free opacity, and so on and so on. So we can't model all these things now, but what we can do is we can ad hoc take into account some opacity in the following way. I'm going to try and model, following this amazing book called Observation and Analysis of Stellar Photospheres, I'm going to try and model H- opacity in my atmosphere, okay? And the way that I'm going to do that is I'm just going to use some expressions that Gray is giving in this book. And basically, again, what he gives there is this super convenient polynomial expression, which gives you cross-section. So cross-section is basically the effective surface of each particle for the collisions with photons, which basically means for the absorption. And what he gives there is basically this sort of polynomial expression, which gives you the dependency only in terms of wavelength. And I'm gonna send a link to the book to you later. Some of you maybe even have it, probably as CU students or other students of US universities. You have access to it in your libraries, maybe even digital ones. So it should be fairly easy to find. And the values of this are something very, very small, right? And if I run this, I actually want to print alpha as well. So the number, this cross-section is roughly for the wavelength that I'm interested in, which is somewhere around the core of H alpha. And keep in mind that this dependency on lambda is very, very small. So I don't have to calculate it separately for each wavelength point in my grid. I can calculate it only for the line core and apply that everywhere. Okay, so the cross section of the for this sort of absorption is something like 2 times 10 to the minus 18 centimeters squared per H minus atom, a molecule actually. So we call it molecule. It's technically an atom, and it turns out that H minus is very good, very important for opacity and emissivity in the solar atmosphere. That's basically just a hydrogen which captured another electron. And then it's the bounding energy of that is something roughly around 1 electron volt. So it's easily destroyed by the photons in optical and infrared. So it turns out that it's very efficient in absorbing these photons. And then there is another chunk of calculations here that you might want to save because it might be important for your further modeling. It allows you to calculate this quantity here, kappa. And kappa is now the effective cross-section per hydrogen atom. So it allows us to calculate, to basically relate the number of negative hydrogen atoms in terms of neutral hydrogen atoms, and to calculate the opacity that way. And what I'm doing here is I'm just using an expression given from the Gray's book, where you basically express this cross section in terms of electron pressure and theta, which is temperature scaled in a convenient way. Okay. And then what I can do is I can finally calculate my H minus opacity by multiplying this kappa, which is now cross-section per neutral hydrogen, multiplying it with neutral hydrogen density, converting to centimeters, and then finally converting back to meters. So now we have opacity of negative ion of hydrogen for the whole atmosphere. And let's plot that. So if we just plot that thing, we don't know what it gives here, right? This could be various. So this amount of opacity doesn't tell us anything. But since we have here 10 to the minus 5 per meter, and we're talking about hundreds of kilometers, 100 of kilometers is roughly 10 to the 5 meters. 10 to the 5 times 10 to the minus 5 gives us optical depth of roughly 1. So it might be okay. So let's now add this opacity to the opacity of the line and see what comes up. Okay, so what I'm doing here is I'm adding them, and I'm using this particular way of casting these arrays here, because now it allows me to add this array, which has dimension only 57 or ND if you want. It's 1D array. It allows me to add this to 2D array, which means for each depth, this expression is going to add opacity belonging to neutral hydrogen to the total opacity. And actually what I'm going to do here now is I'm going to plot opacity at the deepest point, just so that we can see that it doesn't really drop all the way to 0 now. But I'm actually not sure if we will see that, but let's see. This, and then opacity at the last point, which is the deepest point, and what do I fix size? Okay, so you can't really see it here, but if I plug it in log scale, you see that it only changes by a few orders of magnitude. So if this was pure Gaussian, it would continue dropping this way all the way down. But here it saturates roughly around 10 to the minus 4. So there is some extra opacity here now. So what I'm going to do now is I'm going to find the line core, because my next step is I want to compare the optical depth in the line core with the optical depth in the continuum. And this is just a very, brute force to find where is the maximum of my opacity. And it turns out it's the 0.186, and I'm going to call it L core. So cool. I recompute the optical depth here, right? And now I'm going to plot the run of optical depths for the continuum point, which is 0, and for the line core. And I'm getting something like this. Now this makes a bit more sense. So I'm starting from optical depths of 0. So that's why these things are dropping very, very deep at the core. And now they have this very, very similar run. But however, what I'm getting here is that my total optical depth in the continuum is something underneath 10, right? And my total optical depth in the H alpha is almost 10 to the 7. And this is to show you how this illustrates you again how much more opaque the spectral lines are than the continuum. And no wonder that when you look at H alpha images, you can't relate them to what's happening in the photosphere. It's simply because they're sampling such a different height range. Cool. So then again, there is one more tweak, which I don't want to spend too much time on, because I also want to leave you some time to play. And that's, I'm going to additionally tweak continuum opacity according to the fact that I know that I should have tau roughly 1 in the continuum at depth point with 0 kilometers. So I see here that it's not exactly the case. So basically I plot the heights and optical depths for each point in the atmosphere, and I see that roughly at 0, which is somewhere around here, I have still like factor of 20 of opacity missing. Does anybody have any ideas why is it so? So we accounted for H minus, which is the most important species. You hear that in every radiative transfer course. So we accounted for that. We took a respectable book, and we are still not getting appropriate optical depths. We are still missing opacity. Can somebody tell me why is it so? Shoot any ideas that you might have. Are you all sleeping? Non-LT hydrogen ionization, says Ryan. Close, but let's hear more ideas. Not unimportant, but not crucial here, because keep in mind, Ryan, that we are talking about the continuum opacity here, which means that deep layers are still missing opacity, and non-LT effects are not so important there. Okay, so this one is not very trivial. It's actually very subtle. So I'm not going to torture you. I'm going to give you the answer. It might be intuitively from the no. Electron scattering is important in very high layers. So first of all, actually I'm just gonna. We don't have to look at the equation. You can go back in the equation and take a look at it. H minus opacity comes from the neutral ion of hydrogen. In order for neutral ion of hydrogen to exist, we need to have electrons. It turns out that in the moderate temperatures, which means something under 10,000 Kelvin, the most important electron donors, as we call them, are not hydrogen atoms, are the atoms of metals which have much smaller ionization energy than hydrogen. So when you go into the cooler regions of the solar atmosphere, all the electrons are coming from iron, well, basically from iron and few more species. Obviously, we didn't include these things here, as I told you, that then solving these coupled Saha equations would become very, very hard, and we couldn't do it in one code. So we are missing a lot of electrons, which in turn means that we are missing a lot of H minus, which means that we are missing a lot of opacity. Another thing is that H minus is an important source, and if you want to model spectral lines, it's important. But to really model continuum opacity, you need to include other sources, and most notably, it's bound-free ionization of hydrogen. Not obviously from the ground level, because from the ground level you need ultraviolet radiation, but for the upper levels you can ionize them even with optical radiation, and there is a lot of hydrogen, and relatively a lot of that hydrogen is in the second or third level, and then it might be important for our ionization. So, and then it may that ionization causes opacity, and that opacity is missing. So what I'm going to do here in the next line, I'm just tweaking the opacity. So I'm assuming that I'm only accounting for small fraction of H minus opacity. I'm tweaking it by a factor of 20 in order to get reasonable continuum opacity, and so on and so on. I'm recalculating optical depth once again, and I'm replotting this once again, and now this looks like it has a little more sense, and really at 0 kilometers I get roughly optical depth of 1, and that sort of makes sense, right? So this is just very, very hard code tweak just to get reasonable opacity in the continuum. If you model this very carefully by adding additional metals and by adding bound-free opacity of hydrogen, which is now not very hard, you only need to know populations of your appropriate hydrogen levels, you will get much better result. Okay? And now finally I have opacity everywhere, I have optical depth everywhere, I can solve the radiative transfer equation. And what I'm going to do here is now how to solve the radiative transfer equation, right? So first of all, we need the source function and we need the opacity. Actually, we need the source function, we need the optical depth. Optical depth we have just calculated. And the next step is to use the is to use to see what the source function is. In principle, now I should also find a way how to calculate the emissivity of my continuum sources. Then I can add the emissivities separately and opacities separately and divide these things to calculate the source function. So keep in mind that you can't add source functions of independent processes together. It doesn't work that way. Okay, so opacity and emissivity are additive, source function is not. But what I'm going to assume here, I'm just going to assume that the source function is equal to the Planck function. And I'm going to add that command here. By lambda 0, I'm assuming the line core, because once again, I told you that Planck function changes very slowly with wavelength, so I can only consider one wavelength. Now the question is how to calculate, how to do the formal solution. Basically, how we do this is we should integrate, and let me also write that thing here. So the formal solution is something like this. So we know that formal solution at the top is incident radiation plus integral going from 0 to total optical depth at that wavelength. Yeah. Interesting. This is not rendering. Why is that so? Okay, I had an error. So we know that the outgoing intensity is, and I'm missing one term here. Okay, so we know that the outgoing intensity is equal to the incoming intensity at the bottom of the atmosphere times e to the minus total optical depth plus this integral here. And that should give us the result. And in practice, we can often assume that this tau lambda is basically infinity, that our whole atmosphere is very optically thick, and that we can just solve this integral here. In practice, that is not how we solve for the outgoing intensity. In practice, what we do is we start from the bottom. We solve the radiative transfer equation in the first slab or in the first layer of the atmosphere. Then on the second, then on the third, then on the fourth. And we always use the outgoing intensity from the previous layer as an input intensity for the upcoming layer. So and the simplest way to do this, and last year we did more complicated case, so people who are curious can go back and figure out that one. The most simple case would be to assume that each of the slabs is homogeneous and to use something like this. So for one slab, intensity going from a given slab is equal to the incoming intensity at that slab, E times e to the minus optical depth at given wavelength of that slab or layer, plus the some mean source function in that layer times e to the minus times 1 minus e to the minus delta tau. Okay, and we are assuming that the source function is equal to the Planck function. So the way we're going to do that is I'm going to allocate this array, which is going to hold our values of intensity. Okay, it's going to have the dimensions nd for each depth in the atmosphere and for each wavelength. I'm going to assume that at the bottom, my intensity is basically equal to the Planck function, and the justification for that is that the bottom of the atmosphere is just so dense, there is so many collisions, and the mean optical path of photons is so small that basically there is no real radiative transfer happening, right? And I'm going to start from there. So I'm going to start then basically from the next layer, and I'm going to say, okay, first calculate the optical distance at that wavelength. So this is going to do all wavelengths simultaneously between the, basically calculate the optical thickness of this layer that I'm looking at, and then calculate the intensity coming from this layer as previous intensity times e to the minus delta tau plus this b of d plus 1 plus bd times 0.5 is some sort of mean source function in this layer, and finally times e1 minus e to the minus delta tau. And this is going to do it simultaneously for all the wavelengths. And then finally, the only thing that I need to do is I need to transform my valence back to the air and to plot I of 0, which is my incoming radiation. Sorry, I didn't execute this. And this is what we are getting. And if you remember, so yeah, maybe I need a bigger plot. So the wavelengths are okay. And if you remember, this is how the not exactly, but this looks a little bit how like the H alpha calculated in LTE. And of course, the reason why the line is not an absorption line, but is actually an emission line, is because we are neglecting all the non-LTE effects. So what we are getting is we are getting the line which tracks the temperature, or let's say that it tracks the source function. The source function run with the depth. So what I'm going to do now, I'm going to calculate again the source function. And the way, and what I'm going to do now is, you might remember these plots. I'm going to plot the run of the source function with the optical depth at 2 given wavelengths. So what I'm going to do is I'm going to plot it in the continuum. So tau, so this is going to be semilog x. So I'm going to use x-axis in log scale. So tau in the continuum B, and I'm going to call that continuum. And then I'm going to plot at the, it was LC or L core? L core, cool. L core. B label line core, and then we have legend, and then X label is log tau, Y label is source function. This is the plot which we said previously that not log ow, log tau. Cool. So this is what we, and what I'm going to do now is I'm going to do, I need to do a vertical line. This is something like this. Sorry about this. Ax B line. Okay. Okay, there it is. So, and let's set a color. So, this horizontal line tells us where the optical depth is equal to 1, but keep in mind that this is now, these are now 2 different optical depths, okay? One is, I will unzoom a little bit. One is for the blue is for the continuum, orange is for the line core, right? And now what you can do is you can basically say, oh, wow, well, okay, what I have here is that my optical depth equals 1 for the continuum is at some point, and it sees this optical depth, which is lower than the, sees this source function, which is lower than the source function at the point where optical depth is equal 1 in the line core. Hence, my line core is stronger than my continuum value, right? And now this is super bad. There are a lot of things that we have omitted here, and I'm going to list them now, and I'm going to write them down later. So first thing is we considered only hydrogen, which gave us wrong number of electrons because in most of the regions other species contributed to the electron density, right? We neglected basically all the other opacity sources except the H alpha opacity and emissivity and hydrogen minus opacity and emissivity, and we sort of tweaked our opacity of H minus to get ballpark of the reasonable opacity sources, right? And finally, most importantly, we assume that our source function is equal to the Planck function, which for H alpha it is definitely not, and we know that this profile here should not have this emission in the line core, and it should be absorption line. Another thing is that this line is still very narrow. The reason for that is that we didn't take into account damping. Taking into account damping would complicate things a little bit. It's easy to implement. If we have the time today, this is the first thing that I'm going to try and do. But damping would create this line much more broad, but then we have to use Voigt function instead of the Gaussian function to do this. So there are a lot of things that you can improve here using yourself, and I totally encourage you to start playing with that right now or when we finish the class. And some of the things would be, you can add some collisional damping. It can be totally ad hoc, and you would get more reasonable line shape. You can increase or decrease the line opacity to simulate how different lines would behave. So if we have more opaque line, it would pick up even higher regions of the atmosphere. If we have less opaque line, it will maybe even not see this temperature rise, because keep in mind that this emission is happening because the source function is increasing as I go to higher regions here. Let's denote this plot so that we... so we know what we're talking about. So we know that this emission in the line core is because optical depth equals 1, and the line core lies somewhere in the region where the source function is increasing. If it lied underneath that, we would see no emission. And to convince you of that, I'm going to artificially decrease the line opacity and recalculate things again. Okay, so the way where I'm going to do that is I'm going to go here, and I'm going to say, so before adding continuum opacity, okay, let's just do it here so that we know. We're going to make opacity 100 times smaller. You see now. Where is the line profile? You see that now line is very weak, and it's an absorption line. So let's see if I can do something not so dramatic. Maybe. And to be completely, to not break the code, we should probably do the same with emissivity. Oh, but then I need to, Oh, and yeah, and this needs to be, sorry, I did this accidentally more than once. It should be here. I don't like indentation. So, okay, so this is more reasonable absorption line. So you see now that even when I decrease the opacity by 100, so previous result was wrong. Even when I decrease the opacity by 100, we get a strong line with a small hint of emission in the center. Okay, and if I decrease it even more, it's going to be even more reasonable absorption line, and so on and so on. Before I let you play on your own or disconnect or go and cook lunch or do whatever you want, I want to hear some ideas. So you know now, you have seen with your own eyes what influences the line opacity, right? Can you tell me why do now different lines of different species have different opacity than H alpha, or different, or simply tell me what are the properties of the transition and the element and everything that influence the opacity of the line? Okay, cross-section, very good. What would cross-section, abundance of species, also very good. So, Dennis, you said cross-section. What constant that we used here would cross-section correspond to? So remember, for spectral line, we never used cross-section. So what in classical terms is cross-section, for us was Einstein coefficient, right? So here, I'm calculating my opacity. Let me zoom a bit again. I'm calculating my opacity using Einstein coefficients. Larger Einstein coefficients imply higher cross sections. And basically, what we call cross section here would be everything except n. So the cross section would be B23 minus G3 over G2 B3 blah blah blah, whatever times blah would be the cross section. Okay. So cross section is basically opacity per absorber. Yeah, actually, you can't really include stimulated emission in the cross section. Very good. Ryan said abundance of species. Yeah, exactly. Very good as well. So abundance of species would influence how much in total species I have to absorb or emit. If something is very scarce, such as lithium, for example, the lines are not going to be very strong, right? What else? There are more subtle things. Let me do this. Let me increase. So let me first put opacity and emissivity back they were. Let me make another H alpha line where both levels are shifted up by 1/2. So here of electron volt, or let's say by 1 whole electron volt. Sorry. Or let's say 1/2. Okay. So here I'm gonna have 69. Here I'm gonna have 58. Hop, hop, hop. Wow. No, one more. Okay, not strong enough. But you see where I'm aiming at, right? So in principle, the energy levels of the energy of a level determines how populated that level will be. And if I have, so let me see if I can get this. 1, 0, 0. So hop, hop. So the energies of energy levels should, okay, so you need, it's not strong enough. I would really have to tweak the energies a lot. Maybe I can do it now. Okay, I should have tried this. I thought that this is going to be easier. But in principle, you can play with this and you can see it later. If I make my energy levels higher, it's going to make the appropriate levels less populated. It's going to decrease the opacity, right? The same thing goes for ionization. If my species are easy to ionize, I'm not going to have a lot of them. It's gonna make opacity smaller, and it creates all these sensitivities on temperature and pressure and various things, where we see that a lot of things are influencing the opacity of a spectral line, right? And that's, for example, why you have all these situations where, let's say, magnesium 1, which is very abundant species, has this very strong resonance line, and this resonance line is still not nearly as strong as calcium resonance lines or hydrogen resonance lines, because simply magnesium 1 is very easy to ionize, and then there is much more magnesium 2 than magnesium 1, and there is not enough opacity, and so on and so on. So these are all the things that come into play. I'm just gonna show you now one thing. You can shoot the questions now. I'm just gonna very silently code one piece, which is gonna add some collisions to the line shape, just so that you can see how the line changes. And in the meantime, you can ask me any questions that you have.
Hey, Ivan, so I have a question. In the part where you added some artificial opacity to make sure that that Z of 0 kilometers was the same, was at log tau equals 0. How do you know that beforehand? Like, how do you know not to just redefine the height scale to do that?
No, I'm cheating here, of course, because I know that this model is created in such a way that height equals 0 needs to be at optical depth 1. So this is just some knowledge that I know ahead. This is not generally true. No, generally you cannot do something like this. See what I mean?
But like, what if the model itself that you got from is missing some opacity sources or something?
No, of course, but for this one, I'm presuming that it's not, because this is very well known atmospheric model, and we're using that one. Yeah, this is just example that I used here so that we get nicer line profile. I will put a note that this is not something that you generally do. You shouldn't generally just model all your opacity sources and that's it, right? I just knew, because I knew this atmospheric model, and in the atmospheric model there is opacity and height given, and I know that my optical depth is nowhere near that one. See what I mean? More questions? Okay, if there are no more questions, let me just tell you how to do the void. So in principle, what you want to do is you need a new function. So we're gonna import something like this. So void is one of the special functions, and it's there are many ways how to calculate that. I'm gonna use this one here. No, I'm going to use this one here. From SciPy Special. So the official part of the class is done. If anybody needs to leave, you're free to leave. Thank you for being here, and I hope you're doing well. I'm just gonna use 5 more minutes to calculate the void shape. And the people from Boulder, we're gonna have a group meeting after this. So yeah, but whoever is interested to see how the line changes, you can stay and hang online, and this is gonna be recorded and uploaded for people who have to go. So we're gonna do something like this. SciPy Special, import void profile, and then void profile. So I'm gonna use something like this. Let's say profile is void profile, and then the arguments are x, sigma, and gamma. So what I did is I introduced this quantity which we call reduced wavelength, which is basically just distance from the given wavelength to the line core divided by the Doppler width. So this is going to be my first argument. Then in these units, my sigma of the Gaussian is basically 1 because I normalized everything to DLD. And then finally, I need this damping coefficient, where, for example, one reasonable thing to do is 1 to the e to the minus 2. You can play with this later. And then I'm gonna plot this just to see what happens. What kind of amplitude do I have? So SciPy Special. Okay, maybe something like this. Import SciPy Special aspects. Aspects. Okay. Okay, so it doesn't seem that this exists in my implementation. Okay, what I'm going to do so that we don't lose time now onto me hacking this thing with an X is that basically what we would have to do is you would have to call the void function with given arguments. And whoever is interested into trying this to see how the line profile shapes, shoot me an email or let's meet on Zoom tomorrow or any other day, and we can figure this one out together. So I maybe just have to use these existing things in Python to write the void profile. Okay, any questions, comments? Okay, so on Thursday, we're going to do something completely different, right? We're going to try to use Markov chain Monte Carlo to fit some Stokes V shapes to obtain the magnetic fields and the densities. And if we have the time, we're going to even go one step further, and we're going to try and use Milne-Eddington model atmosphere to do the same, to get also magnetic field orientation. So tonight I'm going to post what you need to download in addition to existing thing. There is just one package which allows you to do Markov chain Monte Carlo inference. Yeah, wash your hands, hang out, be good, get in touch with me if you need anything. Take care and see you Thursday at 2 p.m. Mountain Time. Bye.